And so welcome to Paolo Perrone, who'll be talking about joint work with Walter Tolan. Can extensions are partial colimits. So off you go, Paolo.
Yeah, thank you. Do you have any policy on how to ask questions or?
So everyone's muted, but if somebody wants to ask a question, they can just unmute themselves and ask the question. That's the way we usually do it.
Okay, that's perfect. Yeah.
Okay.
Okay. So let's get started. Thanks for having me here. So I was saying before, this work is partly motivated about what I was saying in probability. So maybe we can sketch what happened there at the end. So what I want to talk about is how can extensions sometimes can be seen as colimits of a diagram done partially. So maybe let's see what I mean. Suppose we have categories, let's say C, C prime, and D. We have a functor F, we have a functor G, and we want to take the can extension of F along G. So for example, suppose that, what can I do as an example? Let's say C is a category that looks like this. Maybe let me do it more like this. G is a category that, let's say, just looks like this. And the functor G just maps this, let's say, subdiagram to this point and this subdiagram to this other point. Okay? Now, if we look at their images in D, now a priori, maybe let's make this a little bit bigger. A priori, the image of F will look kind of the same. The image of the can extension will also look kind of the same. And the natural transformation is going to have some arrows this way. Okay? But moreover, in many cases, these things are colimit cocoons. So what does that mean? It means that we had a diagram in D, and we have replaced part of the diagrams with colimits of just that part of the diagram. Okay? So this happens in many cases. Sometimes it's a little bit more complicated. So I claim that this is an instance of what I call a partial evaluation. So what are partial evaluations? So in one sentence, those are the one simplices of the bar construction of a monad. Let me explain a little bit more. So let's go in set for simplicity. So let T mu eta be a monad on set. Take for example the free commutative monoid monad. Like a computer scientist called the bag monad or free commutative monoid monad. So if you have a set X, then we get a set Tx, which is like, so to say, formal sums in element of X. It contains elements like such as X plus Y plus Z and so on. Okay. Now let A E, let's see, E T A be an algebra. Eilenberg-Moore algebra. So example, natural numbers with addition. Okay. So now a partial evaluation. So given A and B in A. Okay, I'm taking elements because we're in sets, but we can do this more generally. Partial evaluation from A to B is an element. Let's call it K. Sorry, not in A. These have to be in TA. So maybe, yeah, okay. It's K in TTA such that, okay, so here we have TTA. We can apply the map mu, the multiplication of the monad to get to TA. And we can also apply TE to get to TA. Okay. So, and you know that the algebra structure map is the equalizer of these two, the back equalizer, the co-equalizer. Okay. So if there's K TTA such that K is mapped to A here and to B here. So for an example from the free commutative monad, so what I want to say, for example, is that, I don't know, this formal expression 1 plus 2 plus 3 plus 4, so there's a formal sum. So this is in Tn. This, of course, can be summed. So we can evaluate this to n, and the result is 10. But we can also say that this is the same as, I don't know, 3 plus 7. Partially evaluating this piece and this piece. A bit like we were doing before with colimits. And how? Well, because there's an element in TTA. So it's a formal expression of formal expressions. So this formal expression, formal sum, whose terms are formal sums as well. Now, mu can be seen as like removing the boxes. And TE, well, inside each block applies the algebra structure maps. So takes those internal sums, okay? So that's an idea of operations computed partially. Okay? All right. Now we want to talk about colimits. So we need to do this on cat. And this will have to be just a pseudomonad. All right. So let's give the definition in our case. So let T mu eta, and there's a bunch of 2 cells, be a pseudomonad on cat. Now, we have to be careful with size issues here because we're talking about free co-completions. So these cat are locally small categories. Okay? Possibly large. So let A, E, and a bunch of 2 cells be a pseudo algebra. Now, given some, let's say, P and Q objects of TA, a partial evaluation from P to Q is some, let's say, phi in TTA object such that mu of phi is isomorphic to P, and TE of psi is isomorphic to Q. Okay, so just like before, but now up to isomorphism. Okay, what is the monad of colimits? So, well, the free co-completion monad is sometimes called the monad of small presheaves. So I think a reference is this paper, Limits of Small Functor. There's another monad, which is a bit nicer, so to say, like it's kind of a, so to say, resolution of this monad, which is the monad of diagrams. Which has first appeared in a paper of Guittard called, well, On the Functor of Diagrams, I guess. It's in French. Sur le functor diagramme. That's in Cahiers, I think in 71. Now, it is claimed that diagrams form a monad in there, but the construction is not very explicit. So most of this work was actually making these constructions pretty explicit. And we will see that Can extensions are partial colimits for both of these monads. Okay. So let's try to see how these monads work now. So the monad of diagrams work pretty much in the same way. So take C, a locally small category. Now, a diagram in C is a functor where the indexing category I is small. Okay, so we just want small diagrams because we want to take colimits of these things. So we don't want our theory to become trivial. Okay. Amorphism of diagrams is I to j. We have some r here, so a functor from I to j together. So if this is diagram D and this is diagram E into C, together with the natural transformation here. Okay. So be careful. Sometimes people, as morphisms of diagrams, just take natural transformations with the same indexing category. This is a little bit more general. Okay. So if diagram D looks like this in C, sometimes people imagine morphisms of diagrams as some kind of, deforming, maybe possibly identifying things in our diagram. So that's the new diagram. But in our case, nobody says that R is essentially surjective. So you have to view morphisms of diagrams as deforming our original diagram into a sub-diagram of the new diagram, because there may be objects of J which do not come from I. Okay. You can view this as a growth in the construction. Like this is fibered over small categories and so on. Okay. So something like cat over C, but lax. Okay, so diagram of C is this category, is the resulting category. And it is again locally small. If we have a functor from C to D, then of course a diagram in C becomes a diagram in D just by composition. So we usually call this F star from diagram of C to the diagram of D. And so diag is a functor. Well, it's even a two functor. I mean, you can also do the same with natural transformation. And so this is a strict two functor, okay? That's one of the main reasons why we want to use this monad, because the monad of small presheaves is weak instead. And this, of course, one can strictify it, but then it becomes not very explicit. So this instead is very explicit and strict, okay? So that's a functor part of the monad of diagrams. The unit is pretty simple. Well, we have an object C of C, and we form the one object diagram. Which picks out the object C. I'm sure you are not surprised about this. Maybe a little bit more surprising is the multiplication. So the multiplication is the growth and deconstruction. Why? Well, first of all, we need something from diag of C to diag C. So what's an element of diag of C? So that has to be a diagram of diagrams. So what does it mean? We have a small category here with objects and morphism. Then here we are in diag of C, which means that, so let's call this D. What does this mean? Well, that means that on objects, this picks out a small category and a functor into C. That's an object of diag C. And it does this for each object. And now for each morphism I, it picks out a morphism of small category, so a functor, and the natural transformation here. Okay, so you see, what are elements of diag? These are the same thing as lax cocoons with tip C, made out of small categories. I mean, let's say of small categories. I mean, except C, which can be large. Okay. So now let's make this very big. Ooh, this is not very nice. Sorry. How do I make it? Let me draw this again in big. So we have that's D0I. Here we have C. That was D1I. D1I prime. here we have D1I. So now, how can we turn this diagram of diagrams into just a single diagram? Well, you probably know by the universal property of the growth and deconstruction that this factors this way. So what does that do? We have a bunch of diagrams in C. We have, I don't know, this diagram in C. We have this other diagram in C. And we have the natural transformation that was like connecting these two diagrams, which will look like this, for example. And what do we say? Okay, well, now take the big diagram. Take the resultant thing, okay? Take the union of the diagram plus the arrows that come from this natural transformation here. That gives you a new diagram in C, which is not just a disjoint union, it has some things between them. And that's why you take the growth and deconstruction and not just the disjoint union, and also not just the colimit, because otherwise you would have to identify all these things connected by a vertical arrow. Instead, we just keep the arrow there, okay? So this gives the multiplication of the monad. Okay. Now, what are the algebras? Well, short answer, I don't know, but I can tell you that co-complete categories are algebras. Not all algebra are in this form. Okay. So how does this work? So first of all, what do I mean by co-complete? Let's be careful with size issues. I mean locally small categories with all small colimits. Okay. So I don't want just posets. Okay, so if this is a complete category, then of course, if you form the one object diagram, what's the algebra structure map? Let me write colim. The structure map is not the colimit, right? It's the choice of colimits. I mean, either you use stuff like cliques or so, but the way we decided to go is just, colim is really a choice of this colimit in the equivalence class, and then they are uniquely isomorphic, so it doesn't really matter. So clearly, a one object diagram is just isomorphic to its colimit. I mean, of course, one may have chosen a different colimit, but they're isomorphic. And more interestingly, the multiplication diagram is some kind of Fubini theorem for colimits, but a very general type. So basically means, let's go up here again. If you have these two diagrams which are connected, then you can either take the big diagram. Maybe let me copy this. Oh, what's going on here? Okay. So you have these diagrams of diagrams. Then you can either take the union and form this big diagram, and then take a colimit of that. Or you can, for each diagrams in the diagram, take the colimit. Which means, let me change color, take the colimit of this and the colimit of this. And now take the colimit of this resultant diagram. And the two things are the same. Of course, up to isomorphism again. Okay. Now you may recognize this starts to look a lot like what we were saying for can extensions. And this is indeed the case. So here's the first theorem. So let C be, locally small co-complete category. Let D from I to C, the cursive, and E from J to C be diagrams, small diagrams. So then let me first say it in a weak way, which is, I think, easier to understand. There exists a partial evaluation phi so which is mapped by mu to D and by T of Collim, not T of Collim, diag of Collim to E. So somehow E is a partial colimit of D if and only if there exists a split up vibration pi into J. Sorry, I was like this, such that E is the can extension of D along pi. Okay. So E is a partial colimit of D if and only if it's a can extension of D. Now you may want to see this is actually pointwise because I and J are small, C is co-complete. So these are the nice kind of can extensions. Okay. The strong form says that there's a bijection actually. So this is not just an equivalence of properties, but it's an equivalence of structures between partial evaluations from D to E are the same thing as can extensions along split up vibration. Now, if you remember that when you have an up vibration, then you can form the covariant growth and deconstruction, then you can prove this pretty much immediately. Like recall that this mu is exactly the growth and deconstruction. So that's pretty much all that the proof says, okay? So that's the first statement. In this sense, for the monad of diagrams, can extensions are partial colimits. All right. But that's not all. Things get a lot more interesting. So first of all, we want to pass through the monad of presheaves, but we have to be careful again with size issues. So let's say this. There's this construction that we call the image presheaves. The name image is motivated by measure theory. It's a bit like the image measure of a random variable. So if this concept is known and has a different name, please let me know. So it's a sort of free colimit. So let D be a diagram, a small diagram. I mean, I has to be small, not C. The image presheaf of D is the presheaf on C given by, I mean, then we have several equivalent characterizations. So first one is this is the unit embedding. And now take the colimit of this thing. So the colimit of this functor. Which pretty much means this, okay? So the colimit may not exist in C, but we take the free one, the category presheaves. Another way of saying this is that we have C op to set, sorry, no, we have C op to set here. Here we have I op, and here we have D op. Now here we take the constant presheaf, and here we take the can extension. That's kind of the same thing. Okay. And you see that one is somehow saying that we are not weighting this colimit. You can do the same thing for weighted, like free weighted colimit by changing this one, or by here replacing the colimit by a coend. In case you have some weighting, okay? But we're not going to talk about the weighted case here. Okay, so here's another new result that we have in the paper. So proposition for two diagrams the following are equivalent. First one is, maybe let's say, okay, let's just call these things. Why is my computer doing this? Sorry. Okay, first one is, these two diagrams have the same image presheaves. So image presheaf of D is natural isomorphic to the image presheaf of E. The second condition is, not only do these two diagrams have the same colimit should it exists, but for every, let's say, locally small category D and functor C to D, then the colimit of F compose D is isomorphic to the colimit of F compose E, if they exist. So but what I mean is, one exists if the other one exists, and in that case, they are isomorphic, okay? In particular, you can take F to be the identity, so this means in particular, these two have the same colimit. 3, so we have exists a zigzag from I to J in the category of small categories such that so together with, let's say, here we have All these are small diagrams. All these triangles commute. And all the functors in the zigzag are confinal. Some people call this cofinal. Some people call it final. Some people call it coinitial. I mean, that thing that preserves colimit. You know what I'm talking about. Like the slice category, the comma category is non-empty and connected. Okay. Now, you probably know that 3-1 is the standard theory of confinal functor. So that's pretty easy. 1-2, well, just take f. No, sorry, not 3-1. So 3-2 is the standard theory of confinal functor. Sorry, I just have numbered things differently than in the paper. This is standard theory of confinal functor. 2-1 is also pretty easy because take f to be the unit embedding up to size issues. The difficult one is 1-3, and where we construct in the proof, we construct a zigzag of length 2. So something like this. And of course, you could just take something like a bit like the Grothendieck constructions, but the Grothendieck construction is large. So you have to take a subcategory in there. But morally, it's like a full cofinal subcategory of the Grothendieck construction of those two things. So this we call D and E when they satisfy any of these three mutually confinal. It's clearly an equivalence relation. And this generalizes the idea of confinal functor, generalizes the theory. But not only that, it also generalizes the idea of absolute colimit. So what is an absolute colimit? Is a colimit preserved by any functor. So if we now take J to be a single object diagram, let's call it X, then the image of just a single object is the unit embedding. The colimit of F composed E is going to be the colimit of Fx. So in particular, X is the colimit of D. But this is stronger. So this is a colimit that's preserved by every functor. And the zigzag condition, you can like redo this construction for the case J has a single object. It basically amounts to say that if you have your diagrams, you have I, at a certain point there exists an I in I such that this commutes, where this is the cocone, this exists. So somehow X is eventually a retract of some of the DI, and uniquely so, in the sense that if it's another retract, then there is a zigzagging here. So we're saying that our cocone is eventually split. Like eventually it has a section, and even uniquely so in some sense.
Paolo, I forgot to say you have 15 or so minutes.
15 more or so minutes. Okay, that is perfect. Okay. So yeah, so this generalizes this idea of mutually confinal, if you want, unifies the idea of confinal functor and of absolute colimit. They're like both part of the same thing that's happening. And these two theorems of equivalence are also pretty much the same theorem. So this result for confinal functor is known. There's this paper by Pare that says on absolute colimit, in the 70s, maybe even in 70s. I don't remember the journal, but it's on Google. So yeah, so this unifies confinal functor and absolute colimits. Okay, now let's look at the last monad. So every sheaf is called small. I'm sorry, my handwriting is getting worse and worse. If and only if, I mean, equivalently in our terms, it is the image of a small diagram. Or equivalently, it is a small colimit of representables. So define PC to be the full subcategory of the category of presheaf whose presheafs are small. And this again forms a monad. So P is a monad, but this time it's fully weak. So P is first of all a pseudo functor and also a pseudo monad. So let's see. I mean, okay, the unit. Let's see. Is obviously the unit embedding. The multiplication I would say the multiplication is the multiplication of the Giri monad in these guys, in the sense that what does it do? So we take phi in here. We have to find the presheaf. So a presheaf maps an object X to mu phi of X. And that's going to be phi of P. So phi is a presheaf from PC, a presheaf from presheafs. And then here I have P of X. And we take this coend, which is actually a very nice weighted colimit. So it's a nice kind of coend. Okay. So what does that mean? Let me use a probability theory now. So this is P of C. We have a bunch of things in PC. You take X, and for each point in here, P, you take P of X, and then pretty much sum them all up together. Okay. Compare with the Giri monad. if you have like a measure over measure of spaces, then you get mu you have now something that maps a measurable space, a measurable set, sorry, to this integral. You take the measure of the set for P, you have this measure over measures. So you weight this by mu and then take the integral. Or, I mean, usually people write this. So it's basically the same thing, okay? And I feel like this is probably one of the reasons why we write coends with integrals. And in case the coend is actually a weighted colimit, this is actually very, very similar, okay? Okay, so I hope I don't have to convince you that this is actually the co-completion monad. So algebras of P are the same as co-complete categories. And in the sense of before, okay, with small colimits, you probably all know very well that if you take every colimit, then you have the whole category of presheaves, but that's not a monad because of size issues, okay? But if you restrict to just small colimits, which is usually what you want to do when you talk about co-completions anyway, then it is a very nice monad. I mean, weak, but it's not like a relative monad. It's just a higher dimensional, okay? Algebras are co-complete categories. Maybe a way to see that is that structure maps are coends. So you have P, C, sorry, this P, and you have this thing. This is P of C, P of X, sorry, times, this is the tensor or copower times X, okay? Again, compare with the Giri monad, where you have like probability measure is mapped to just centers of mass or averages, okay? This is really like the Giri monad.
Can I ask you one quick question, actually?
Sure, sure.
So in the case of P, that map from PC to C is a, well, it should be a left-hand extension of the map of the identity from C to C along the unit.
Yes, it's true. So has to do with the fact that P is laxide impotent, or
Yeah,
like.
So I guess I was going to ask. So that's a sort of, I don't know, global universal property of P, and I was wondering if you can say anything similar about the Geary monad, if there's any.
Oh, I see. No, I don't think so. I mean, mostly because we don't have any two-dimensional structure
I'm just curious.
on the category of measurable spaces.
Okay.
But to be completely honest with you, I've been looking for such a thing for, I would say, years now. So I think there is something, but it's really hard to, it's probably not the two-dimensional structure, it's something else, but there is something in common. You're absolutely right. I was not able to make that precise though.
Okay, thanks.
But so P is not laxally important, and also Diag is not.
Diag is not laxide impotent.
No.
Okay.
No.
That was
It's explained in the paper if you want to see why.
Thanks.
So in some sense, Diag is nicer, but in some other sense, it's not. Okay. Maybe if you want to see why this colimit exists, because C is not small, we can see like also maybe how it works. That this is these are the same algebras as before. We can have that P is a small presheaves. So there exists a small diagram here, a small, yeah. Okay. Now I claim that if you take im of PC and now take the coend, this is the same as a colimit up to isomorphism. And since we started with a small diagram, then this co-end exists if and only if this colimit exists, but the colimit is small. And the reason why this holds is the famous co-unit dilemma. Because the co-end of now P of X is the image of D. So that's this is tensor X. But now we can apply Fubini, which removes the brackets. And we can apply the co-unit dilemma. And so we can take these things integrated, and this is just going to be of di, which is just the colimit of di. I mean, colimit in I. Of di. Okay? So this exists. And the fact that algebras are algebras is part of another statement that says, I mean, not theorem, right? Proposition. The image is a morphism of monad. I mean, is a pseudomorphism of pseudomonad. And you probably know that if you have a morphism of monads, then you also have a pullback of algebras. So the algebras of P become algebras of Diag canonically. Like if you have PC to C, then you map it to Diag C, im PC to C. This is sometimes called the restriction of scalars. This apparently was not known for two-dimensional monad, but we proved in the appendix that this is indeed the case. So also for fully weak pseudomonads, we have this restriction of scalars construction, okay? And that's why, if you want, structurally speaking, co-complete categories are algebras of Diag, but not every algebra of Diag arises as well. Okay, so morphisms of algebras preserve partial evaluations. So here we have, I mean, let me say im. Of course, there's two ways of defining this im, up to isomorphism, because we have only pseudo-naturality, but okay, up to isomorphism, this functor is defined. So, and then these things defining our partial evaluations, which are mu here and TE here, which in this case means P colimit, sorry, P of coend and Diag of colimit. Sorry, here it's these things commute up to isomorphism here because it's a morphism of monads, I mean pseudomorphism of pseudomonad, and here pretty much for the same reason, basically by definition of these things are. And so to say, im preserves partial evaluations. Now, a big part of the paper is proving that, okay, im This is essentially surjective on objects by definition, because PC is basically the image of this in the category of presheaves. It's not clear if this is essentially surjective, because there are some size issues involved, but it is. So not only are partial evaluations preserved, but every partial evaluation for P arises this way. Arises from a diagram of the diamond. So I will not talk about the proof of this theorem because it's rather long, but of course you're welcome to ask or to look in the paper. Because of that, we have another theorem that says, let P and Q be small presheaves on C, where C is again co-complete. So remember that before, with can extensions as a partial colimits, we had a strong form and a weak form. Here, we only have a weak form, so P is a bit less nicely behaved. We say that the following are equivalent. A is that there exists a partial evaluation so again, somehow P is a partial coend of Q, or partial colimit of Q in this like weighted sense. This happens if and only if there exists diagrams, small diagram cursive and J and the functor this time we don't require this to be an off vibration such that E is the last extension of D. Okay. So what does this mean? Intuitively, this means that Q is a partial colimit, partial weighted colimit, partial coend of P, if and only if these presheaves are images of diagrams which are one the can extension of the other. Are one the can extension of the other. Okay, for the free co-completion monad. So of course, again, pointwise and pointwise left can extensions. All right. So in this sense, so since this is a free co-completion monad, so this is really the monad of colimits. So these are like really the partial colimits in some sense. So we're saying that can extensions are partial colimits. Because like evaluating partially a colimit is pretty much the same thing as taking the can extension of the diagram of which you are taking the colimit. So in this sense, can extensions are partial colimits. Just to conclude, why was this motivated by probability? Because we've already seen how much P is like the Gire monad. Partial evaluations of these are like partial expectation values. And indeed, instead of can extensions, you take conditional expectation, which is again something like you have two random variables here into an algebra, say real numbers, and the map here, and you're saying that this diagram does not quite commute, but you take the best approximation to making it commute. Like in probability theory, this is given by the can extension by conditional expectation, and it's a diagram of exactly the same shape, and it's again a partial relation, but for probability monads. So in some sense, if coends are like integrals, then can extensions are a bit like conditional expectation. And that motivated this work because I wanted to see if what was happening in probability had a categorical analog, but the categorical analog was not there. And that motivated this work. Okay, I think I'm going to stop here. So if you want to know more, the paper is me and Walter, and it's called the can extension or partial colimit. It's on the archive. And yeah, thank you very much.
Thank you. So as usual, we have our silent round of applause. And whoever, so thanks for a very nice talk. That was great. And
thank you.
If anyone would like to ask a question, go ahead. Maybe I'll ask a question actually. You go back to the last slide for a second.
Yes, let me share my screen again. Yes.
I think I'm just a little bit lost. So in B, there's no mention of any P or Q or anything.
You are absolutely right. So I meant such that P is the image of D and Q is the image of D.
Okay. Okay.
Oh. Yeah, of course. You're right. Absolutely. Sorry.
Okay. And then my other question was, I'd never seen this diag pseudomonad before. And I was just curious it's very curious what its algebras in general are.
Oh, I wonder too. So I've also never seen it before. It's just claimed in this paper by Guittard, but it feels like nobody else.
Hello, I think I've slightly lost your.
Caught on that. So the monad of diagrams. Yeah. Hello. Can you hear me?
Hello, I can hear you now.
Can you hear me?
I can hear you now. Yeah. Hello.
Okay. I guess the connection has a bit been funny, but is it okay now?
It's okay now. Yeah.
Okay. So co-complete categories are algebras. But it seems that there's a little bit more. So it seems that, for example, if we put this in two categories, then categories which admit all lax limits with the structure map now not taking the strict colimit but the lax colimit also are algebras. So I feel like maybe there's some kind of two categorical thing in here going on.
Okay, because it's also interesting that, I mean, the multiplication for the monad is the Grothendieck construction, right? So
exactly, which is kind of a free lax colimit in some sense.
Yeah, it feels like it should be some sort of higher dimensional lax idempotent pseudomonad. I don't know. I don't know. Just there seems like it's certainly determined by some universal property. I don't know, but it's interesting.
Yeah, it's not quite lax idempotent. Yeah, so it's not lax idempotent. I don't know if there's such a thing as lax idempotent, but if there is, then it should be something like that.
Yeah. Maybe you could capture it more easily if somehow via double categories. I'm not sure. That's just an idea. This.
What would be the other morphisms? Could be something like categories and profunctors, maybe.
Something, I'm not really
Functors and
sure.
profunctors.
Sometimes you can just capture some, you can sometimes use double categories in this way to capture some apparent universal properties that at the two-dimensional level for two categories are sometimes hard to capture, but I don't have anything precise to say about it, but if any, yeah, I'll think about it a little bit, maybe.
Yeah, I would love to know. I've been wondering what the general algebras are.
Yeah.
But yeah, it has some kind of lax colimit kind of flavor.
Any further questions?
Can I have one? So, do I understand it well that if your diagram has a limit in your category C, then the map of this diagram D at this map image is represented by the limit of this diagram?
Could you repeat your question? Sorry.
Yeah, sure. Could you go back to the definition of this image map?
Yes, absolutely. Why is my computer doing this? Here.
Yes. So if your diagram D has a limit in your category C, then is it true that this pre-sheaf, column, home, and so on is represented by this limit?
Not quite, because no. First of all, do you mean limit or colimit? First of all,
I mean limit, because the dual of this expression is usually written as the pre-sheaf, which is represented by the colimit if the diagram has one.
I think it's the other way around, like, because a home functor preserves limits, but not colimits.
Oh yeah, probably. That's
so this the home functor turns, like, if we had a colimit here, then this would become a limit outside here.
Yeah.
But we're taking the colimit in the variable I, which is the right slot. And here all limits become limits, but nothing becomes a colimit unless we have, I mean, unless we are in the situation of absolute colimits, maybe that's what you're asking. Here, where, I mean, in this case, we're basically saying that X is the colimit and the colimit commutes with the home functor. So maybe this is what you were asking. I don't know.
Oh, okay, thank you. I just, yeah. Right.
So I feel like so when this happens, so when this is the same as then this is exactly the situation of absolute colimits. So it's somehow the nice special case. But so not in general, but it's nice when this happens.
Thank you.
Thanks for the question.
Any more questions? Well, if not, then let's thank Paolo again for a very nice talk.
Yes, it was
Thank you
very
for
nice.
having me here. Thank you.
And,
Sorry, now I have to leave. Yes.
No problem.
Bye.
Thank you. Thank you. That was very interesting.
Thank you.
And so we can, so I'll just mention, next week we have Charles Walker, who'll be talking about some new work on distributive laws for pseudomonads and decagons, if I remember right. So I'm very curious to hear about that. So we can stop recording.